Okay. Well, okay. So I want to talk about arithmetic progressions. Arithmetic progressions in primes. So I will start by reminding you what an arithmetic progression is. So basically, this is the motivating question. Let me use this. So motivated question: can we find arithmetic progressions in primes? Well, now is the time that I turn to you and ask, well, can we? And you say, yes. There's the green. Okay, so there's the famous theorem of Green-Tao. So the answer is yes. This is the well-known Green-Tao theorem. There exist infinitely many arithmetic progressions in primes, and once you know that, then some natural questions start popping up. So, for example, you can ask, well, if I know that there are infinitely many, then how many? How many do I have? Well, infinitely many. Kate, right, fine. Can we find, so we will denote this by, this is an APK. So this is an arithmetic progression of length k. So we fix k, and can we find, yeah, thanks for infinitely many. Can we find infinitely many k-term progressions in primes? Well, of course, you answer how many, and you say infinitely many, and that's the same question as, if I started with asking you how many primes are there, and you say, okay, about for about 2,000 years now, we know that there are infinitely many, and I ask you how many, then you say infinitely. then there's then I would say, okay, we know some more than that, and there's the prime number theorem tells us that how many, we can answer this how many question in a good way. It tells us that we have roughly n over log n primes up to n. And by now we can answer how many arithmetic progressions of length k we have, and say with a and r smaller or equal than n. So we know how many. So actually we can calculate asymptotic. So this is a large piece of work with some papers of Green-Tao and a paper of myself and Green-Tao. So this is one question you can ask, but another question you can ask is how small can you take this R to be? So how small can R be? Now, number theorists have conjectures related to that. So you can ask, given any, so if I fix R, can I find arithmetic progression with gap R? Then the Hardy-Littlewood conjecture, would tell you that unless there is some silly reason that you can't, so for example, obviously if I take R equals 2, then I can't find arithmetic progressions of length 3. Right? Because if I take a plus 2, and a plus 4, then one of these numbers is divisible by 3, then clearly I can't. But if there's no not stupid, but if there's no divisibility problem, then I can find, so if R is greater or equal than 6, then, maybe not, okay, there are some other restrictions, but I can find a 6-term progression, then can find a 3-term progression. I can even tell you what this is. I thought about it on the bus. Right? So 5, 11, 17. Right? They're all primes. Yes. So I can find, but the Hardy-Littlewood conjecture tells you that there are infinitely many such, and and you could actually predict what the asymptotic number should be. And in general, for any k-term progression, so long as there is no kind of divisibility problem, like in this case over here, then there's a set of conjectures that tells you how many that you should expect to find such progressions, and how many of those should be. But but those are conjectures. So we want to know what can we say non-conjecturally. So if you've been following kind of exciting developments in number theory, you would know that by now we can say various things about, well, until about 2 years ago, we couldn't say anything about even bounded gaps between primes. But by now, the theorem of Zhang, and for bounded gaps between primes, and the theorem by Maynard, and later independently Tao and polymath, then there are infinitely many bounded intervals, infinitely many k-tuples. That's only one p, right? K-tuples of primes p1 through pk with pk minus p1 bounded. So there are infinitely intervals containing k-tuples of primes, and if you try to go through the argument and see, okay, maybe if I had sufficiently many such primes in an interval, maybe I could get a progression from that, but they're too sparse, those k-tuples. This dependence here is too bad to give any, so no chance, or at least at this point, there's no chance to get progressions from this. Well, maybe no chance is a bad thing. So maybe you can use these methods to do something like that, but no obvious way to proceed in this way. So, so what I want to talk about today is, we have these two kind of types of methods. There's the Green-Tao machinery or Green-Tao method that I want to try to. What I want to do today is to try to understand how far we can push that for this question, and then, maybe one of you can come at some point with an idea how we can push it from below and maybe combine something to get, to get better estimates for how small this R can be. So the basic question I want to talk about today is how small can R be via the Green-Tao type method. So I'll call it type method. I'll try to explain why I'm calling it this way. I'll do that here. So I should learn how to use this board a little better. Okay, forget it. Okay, so the Green-Tao theorem tells us more than just the existence of arithmetic progressions in primes. It tells us that it's true for any subset of positive density. So if A is a subset of the primes of positive relative density, okay, that just means that in the intersection of A with the primes, the intersection of A with the interval between 1 and n divided by the intersection of the same set of primes with this interval, this is greater than some delta, which is greater than 0, then A contains APs. This is the method works not only for primes, but works for any subset of positive relative density in the primes. And if this is what I mean by the Green-Tao method, so what I want to ask is how far can we push a theorem for this type of theorem? If we take the subset of the primes of positive relative density, how small a gap can we expect to get, or can we ensure that we can get inside inside the set A? Okay, so this is the question I want to focus about today. Right. So there's a way to show what an obvious lower bound for this can be, and then you can see why I can't hope to take R to be bounded in this type of question. Yeah. Well, that's the method, but the method would say this set of primes would sit inside some pseudo set, if you want to call it, and any subset of and it would sit as a subset of positive density, and therefore any subset of positive density in P would be also in positive density in that. So
we're really not just interested in primes and their subsets, but also in slightly larger sets which contain the primes.
Right. Yeah. You can apply the same, but this is right. Of course, you're right, but maybe this is yeah. Okay. I'll just say. Right. So there's an obvious lower bound. So I claim. We can't take R to be too small. Let me phrase it. Yeah. So for any epsilon greater than 0 that is sufficiently small in terms of k, so fix k in terms of k, I can find a subset A of the primes of positive density with no arithmetic, no non-trivial APs of length that is smaller, R, that is smaller or equal epsilon times log n to the k minus 1. And the reason that's true is that you can just, so how does it work? So why? You can just take, there are not that many primes. I can just toss out if I take all these arithmetic progressions of this size and I toss them all out, I can still, if epsilon is small enough, I will still have a set of positive density of primes left. Okay, so the reason is toss them all out, toss all APs of length at most epsilon log n to the k minus out, and so I toss all the primes that are say any prime that is the first element in such a progression, I toss it out. So I toss all of these out, and then still lots of primes left. Still lots of primes left. Well, I can do, taking epsilon sufficiently small, I can stay with at least half the primes. So say at least half n over log n primes left. And then to take this set or any subset of it would be fine. Yeah?
You wrote APs of length are smaller. You mean AP of difference smaller?
Not of length, you're right, sorry, of gap. Did I, every length is gap. I'm sorry. When I phrased the question at the beginning, did I do it correctly? Okay. Okay, sorry. Yeah. K is my length. K is fixed K is always the length of my progression, and it's fixed forever. So I can still have some primes left, and the way you make this calculation is that finding lower bounds for the number of primes in arithmetic progression is a very difficult task, but finding upper bounds is kind of a classical number theory relatively soft number theory. So if you just need to toss them all out, then you can toss an upper bound of the number of them out and still stay over here. So this is not difficult to see that you can do this. On the other hand, if I take a random set of primes, so if I take a set of with inside the interval 1n of density similar to that of a prime, so if I take a random such set or so, then almost all such sets would have the property that that they would contain arithmetic progression of size some big C times log n to the k minus 1. So on the other hand, if for any epsilon and delta greater than 0, if with probability that is greater, p greater than 1 over 1 minus epsilon, a set of random primes and for a set of random primes p, any subset of it of size of relative size, relative greater than delta will contain a APK of length some big constant C of epsilon delta times log n, not length, gap, to the k minus 1. Okay, so one can, to show this type of result, then use methods of Conlon, Gowers, or Schacht. Do I write his name right? Maybe. Or Samoti, yeah, probably. No. The constant here is the everything depends on k, but yeah.
And when you say random primes, you mean you're choosing a set?
I'm choosing a set with each element is inside the primes, this random set of primes with probability 1 over log n.
So one is being chosen independently from all the rest.
Exactly. Yeah. So yeah, that's what I mean. A random set of primes. So what do we hope to get? So this kind of tells us what we hope to get. So we can't beat this. This is roughly the scale that we expect to get. And here's what we can show. So the theorem, just joint your work with tau, is that we can have gap confined gap of size at most log n to some big power L. Yeah, so this L depends on k. Okay, so we have some fixed number. L depends on k. We would want this L to be k minus 1. We can get a poly-logarithmic bound for this thing. Maybe yeah. So it would be nice to be able. We can't at this moment push our methods down to the optimal k minus 1, but something like k 2 to the k minus 1 or k minus 1 2 to the k minus 2 or something like that. And maybe for 3 we can do better than this. And I don't remember once we couldn't get the optimal one, I lost interest in calculating exactly this. But
exponential and not
polynomial. Oh no, it depends on
N of k you want it to be like k minus 1?
Yeah, right. Okay, that's not what I meant by yeah, but I meant by power logarithmic, by power log. We can get a gap that is power log. So the original Green-Tao theorem, GT gives lil low of n gap. Is that, who asked me, is that okay? Right.
So you're not even close to having
No, and yeah, so we're not close. So good for all of you to work on this and get better results. Let me just mention that we can also do that not only for arithmetic progressions, but also for polynomial progressions. So same for polynomial progressions, which are creatures of the type a plus p1 of r, a plus p, say k minus 1 of r to keep the length, this length k, doesn't matter. So pi are polynomials, integer polynomials. Then we can have the same, only in this case, this L will depend on not only on this set of polynomials, but also on the density delta. And this is just a byproduct of our methods. So this should definitely not be here. So when delta is the set of the when delta is the density of our setting. Okay, so we can't do better than but we can also get a similar type bound for that. Yeah.
What property of the primes except the density is used in all these?
I will get to that. So actually, very as opposed to the other direction, coming from trying to find bounded distance, this is kind of a very soft property of the prime, the same that are used in this kind of y, this kind of upper bound for yeah. Okay. So questions so far? So well, I wanted this talk as kind of an excuse to talk about decomposition theorems. So this is the way I view kind of the philosophy of this type of these type of results, and the decomposition theorem or decomposition result philosophy comes from has its origins in ideas from ergodic theory that come from Furstenberg's proof of Semiretti's theorem. So what is the kind of philosophy? So the philosophy. Do you write? Why? That's I, right? Yeah. It's, this is why I can't have this videoed. So just kind of embarrassing. At least maybe I won't have my kids see this. Okay, so the philosophy is the following. So suppose you want to calculate some average. So you want to calculate some average. And so here's the test case we're going to take. So we look at this average. So this will denote an average, and we're looking at some function f of a plus r, f of a plus 2r. And we take a to be smaller than n, and we take r to be smaller than some h. This is our h is the gap that we allow. Okay, and this is the type of thing we're looking for, and maybe we'd look at for this function f, which is 1a. So this expression over here would count how many 3-term progressions I have in here. So this function f could be very complicated. The set is complicated. I have no idea what I can say about it. But I can look at this average. I can rewrite it as the inner product of the function f with this other function d2, which I'll denote d2 of f. So d2 of f is a function at the point x is the average over f of x plus r, f of x plus 2r. Okay, so what I want to understand, so this is just this expression over here is just, I just rewrote it in this way over here. So here is the philosophy. F could be very complicated, but this operator D, I have this averaging operator that is applied to this function over here. So it takes a function f and composes some average out of it. It could very well be that while the function f is very complicated, this function is simpler. Okay, and here is, oh, okay, so this is, so the idea is that many times, I'll say in simpler, and it can have many forms, but the function d, or this, or not many times, or it could, well, in this case it really does happen, but after averaging, the averaging operator, averaging operator results in a simpler function. So if you think, suppose this were true, suppose in some way this function that sits over here is in some way simple that we can view in many contexts in very different ways. Then it says here that my function f correlates with this simpler function. Then I can try, so the idea would then to be to try to decompose f. So then what we want to do decompose f into its projection and onto all the space of all simple functions. So write f as a sum of two functions, where this function g is what I want to think of as the projection of g of f onto some subspace or something. I don't want to say well, it's not exactly maybe subspace, and something close to a subspace that is generated in some way by the simpler functions. So I want to collect all the projection here onto the simpler functions, and h, so we'll denote this, say this thing, we'll denote it by, say, f, and this collection of functions over here, and this function h will be orthogonal, small, will be orthogonal to this collection. So I decompose my function. If I have something like this, I can decompose my function into the projection onto the simpler functions plus something that is orthogonal to that. So here's, let me show you here's like the most trivial manifestation of this. But the idea is there. So suppose you want to calculate just the average of f of x. Okay? If I just want to calculate the average of f of x, this is the same as f, the inner product of f with the constant function 1. Okay? Then if I want to calculate this, then I could first project f onto the space generated by the constant functions. That's just the constant function. But what is the projection of f onto the constant functions? It's just its average. So this is the same as the average over f. Now I think of this as the constant function, not as a number. So this is the constant function. And 1. Okay, this is the same, but this is just a constant, and which is just the average over f of x, which I started in the first place. But the idea is that if I want to calculate this, I could first take my function f and project it onto the space of constant function and then calculate the inner product. So this is what I want to do here. I first want to take I want to calculate some average. I want to first take the function f, project it onto some simpler space, and I want to say that the average, so then if I have this type of decomposition, so that type of decomposition that I have over there, so what is the, then what I get is that f, say d2f, this is for the average we were looking at, then this is the same as g plus h with this d2f. But h is orthogonal to all of these, so it's not going to contribute anything. So this is the same as g and d2f, which is not quite the same as g and g. Well, I would want it to be, if I'm lucky, if space chosen well, then I can repeat this, replacing the roles of g and f in the average over there, and finally get it to be more or less equal, well, not exactly equal, more or less equal. Well, this is, g and d2g, which hopefully I can calculate. So philosophy, you have a very complicated average to calculate within some big space. You don't have no idea how to do that. Perhaps if you are able to analyze your averaging operator, perhaps you can see where these creatures, where they have some better, they sit inside some strictly smaller subspace of functions that is better understood, and in which case you have a chance of calculating your average by calculating it for this projected function in this simpler space. So this is the philosophy I'm trying to sell to you. So you should think of it as the model you should have in your mind is something like you have the model in ergodic theory that comes into mind is that you have some measure space, and you have this averaging operator, and this averaging, and you have some other space down here which is simple. This is simpler in some sense, or has a simpler form, and your averaging function takes functions from up here to functions that, so my averaging, a average of f, is a function that if I lift it, well, I should write it, maybe. If I lift it, my function f goes to some other function, which lies inside, I don't know, maybe, sorry, let me, average f is a function that is lifted from y. Okay, so if I have functions here, and if I have a function here and I have a map from over here to here, then I can view any function down here. If f is a function on y to whatever, then I can view f as a function. I can lift f to a function, to a new function f from x to r via this new function is f composed with pi, right? So this is the picture you should have in your mind, is you have this big X up here and you have a smaller subspace down here. This averaging operator takes functions from over here and makes them into functions that are lifted from functions from a simpler space. So in the case that I wrote before, in the averaging case, then you can think of the space X as being whatever you want, and this space over here would just be a point space. The functions on the point space is a constant. And in this case, if you start with functions in L2 of x, then you can think of L2 of y as sitting naturally inside L2 of x. And you take a function here, you project it onto here. This is why I want to think of it as a projection. Okay? So the question is, the decomposition theorems, the role they play is in trying to make this type of scenario in the approximate world. We don't have, except for this trivial case, where they have the average. I can't tell you exactly where these averages A2 look like, what these averages that correspond to three-term progressions. I can't tell you exactly, give you a nice, very nice structure, but I can approximately tell you where they sit. And this is the idea behind let me see if there was something else I wanted to say about this, about decomposition theorem. So what do we want? Right, so what is this? The strategy is first is to prove general decomposition theorem. So for this, one needs the notion what would be an approximate projection. So you want something that would play the same role as the projection operator over here, that I can take functions here and project them down here. So what would play a role of what would we want from this projection? So what do we want from the projection operator? In order to make any of these type of arguments work, what we want from this projection operator, especially for the Samorady argument case, is we want to take positive functions, and we want the projection to also be positive. So what are properties that we want? Properties that we want is that if f is greater than 0, then its projection, I'll denote it in this way. So G would be, that's G. This, I'll call it pi star f, just to philosophically think of it as a projection. We want this to be positive as well. And we want that if f is bounded, then we want its projection to be bounded. And we want another, and the third property that we want is that we want if the integral, we want the integral of f, the average of f, to be the same as the average over the projection of f. Or if not equal, maybe approximately equal to that. So these are the three properties that we have. If you have a vector space and you have some subspace of this vector space, and you have this projection operator, it satisfies these three properties. If you take positive functions, and then the projection is positive. If you take bounded functions, the projection is bounded, and the integral remains the same. So this is one thing, and the second thing we want. So this is one thing we want, and the second one is find the right class of functions. To project on. Okay, so first one wants a general decomposition theorem, tells you when you can have a decomposition, and the second thing you want is to understand where these, or have sufficient understanding to where if you project if your class of functions is not simpler than the original class you started out with, then you haven't improved your situation in anything. Okay, so what do we have in our case? And what is the, well, maybe before that I can just say what is the decomposition theorem? So decomposition theorem. So this is not in this formulation, but it takes its sources in the original Green-Tao paper, and then paper of Tao and myself, and then the paper of Gowers, and the RTT, the four Reingold, Trevisan, Tulsiani, and Badan. And the decomposition theorem, the form that I want to use is the following. Right. So let f be some collection of functions f from bounded functions. X for me is whatever I can start with the interval 1n, or with any other. This theorem would work in general. So I have some collection of functions from x to -1, 1 that is closed closed under multiplication, so if I have pointwise multiplications, so any two functions in here, then the product is also in here. So this conceptually looks like an algebra, but I can't. I'm allowed. So all my products are inside, but I can't allow infinite long sums. Okay, not infinite, but as the lengths of the sums I don't want to be included. I don't force them to be in here, but I do. Yeah. So it's closed under multiplication. That containing the constant function, containing the constant function 1. So I want the constants to be inside. Then, right. Yeah. And give me, epsilon be greater than 0, then there exists some epsilon prime greater than 0 such that, I'll write and explain, if nu is a function from x to minus 1, not necessarily, sorry, if nu is a function from x to 0 infinity, such that nu minus 1 is orthogonal to f, okay, if I have a function nu that is nu minus 1 is orthogonal to any element f in this algebra, then
What's your inner product now? Now it is something formal, so, right?
yeah, right.
It's not just philosophy anymore. So what is the inner product?
Yeah, sorry, it's the sum over f of x, g of g bar x, x and x, or whatever, usually it would be an average. So x would be some finite set, and this would be this average.
This would work just as well if x were a measure space and you're taking the normalized.
Yeah, this is very general. Yeah. Yeah, then I didn't write, so I wrote if this, then for any, so maybe this is a bad notation. Let me write this f as big F, so that, because I used a little f for what I want. Then for any f that is between nu and 0, we have the decomposition. F is equal to g plus h, where g is bounded between 0 and 1, and let me write and then h f is smaller than epsilon for any f and f. So I wrote this down, this kind of a long thing, but I want to explain the way you should think of this theorem, okay? What this theorem tells you is, suppose you're in this context, you have this very special function nu that satisfies that satisfies the property that if I subtract 1 from it, so first of all, just from this property over here, I see that this nu has average 1. Can you see that? This is just because the constant functions are in here. So the average of this function nu has got to be 1, asymptotically, well, approximately 1. So this is I have some function nu with average 1. It's not necessarily bounded. Okay, so it's not, well, it's necessarily bounded because x is finite, but it's not 1 bounded. And it satisfies the property that it is, this nu minus 1 is orthogonal to this sigma algebra. So I think of f as kind of this f over here, this collection f that is closed under multiplication. I want to think of it as kind of a sigma algebra of functions. And I have this function nu minus 1 that is orthogonal to that. Then decomposition theorem here will tell me that for any function that is bounded by nu, I can decompose it into a sum of two functions. One of them is properly bounded by 1, and the other one The other one is approximately orthogonal to this sigma algebra. So how do I want you to think about this? Well, suppose I have this function nu that I start out with. Nu is a function in L11 of x. So I'll write it this. So this is a function, the average over nu is approximately 1. Okay, so L1 is average and 1 is radius. L1 norm smaller equal than 1. So nu L1 is more or less, well, I should write approximately 1. Okay, so I have a function in L1 of x. Okay, in the unit ball of L1 of x. Right, yeah. And what this theorem tells me is that if this function satisfies this property, then my decomposition theorem tells me that I can take this function f that is bounded by this collection of functions in L1, and I can evaluate whatever thing I will want to do on this collection of functions which are bounded functions. So I'm projecting, so the projection here is to some subspace of L infinity 1x. Bounded functions, so I started with L1 functions and ended up with a bounded function. Okay? This is the way one should think of this theorem, is that I started with a large class of functions. Those were just much bigger class of functions. Those functions that are just average 1. And now I'm in a much smaller collection of functions. These are functions that are bounded by 1. Okay, and my property is the same. So this projection satisfies all these properties that I want. If I start with a positive function, I ended up with a positive function. Did I write that f is? Yeah. I started with a positive function. I ended up with a positive function. And if I started out, and the average of f is approximately the same as the average of, why is that? Yeah, automatically, again by this property that h is orthogonal to f, I get that the average is roughly the same. Okay, so how do I apply it to our situation? Okay, so this is the picture I had before. This is my big X, and this is my smaller subspace. Okay. So now it's the only remaining problem is to correctly choose the collection of functions. So what would I want to choose? Well, I wrote to you these. So what should f be? What should f be for our problem? I told you what our problem is. Our problem for us, we are calculating this average of f of x plus r, f of x plus 2r, and this r is bounded by this h that I took before, and x runs over everything. And f for me is the characteristic function of my set A. Not exactly. So for me, I need to normalize it by log n to make the average of positive density inside the interval. So I take a function f. This is my function f. What I want to take, what I would have wanted to take f to be, is this collection of functions of the form f of x plus r. This is what I said before, right? If I could take this collection of functions, these were the D2s I wrote before. This would have been great. Only some problems. So first of all, you have to modify this a bit. So in order to, I told you want to shift the average around, so I have to allow a few functions over here. So this would be fine. This collection is not quite closed under multiplication. So if I take a product of two of such functions, then it's not of this form, but it's actually a convex combination of things of this form. So if I'll take the convex hull of these guys over here, then I'm already in a good situation. There's only one problem that is really a big problem in our situation. well, I should say that there is, if I take this collection, there is a function for the primes. For primes, this is the only number theoretic information. For primes, there exists such a function nu that satisfies not quite, that satisfies that nu minus 1 is orthogonal to this f, but not quite this f. So there's one problem, then this is the problem where this short interval comes into place. The problem is that when you take these elements to be small, this range to be small, then these functions are no longer bounded. If I take R to be in the range of the full range of the full interval, then this by easy number theoretic arguments, these functions are bounded. But if R is not, it's just bounded by this logarithmic bound, then these functions are, you can show they're actually not bounded. Yeah. This nu? Well, I want to say that there is a function nu that will satisfy. So what will it satisfy? Let me write what it satisfies. But it is true. So it's not true. If I take functions f here, f1 here, and f2 here, what I want is this: f1 and f2 are bounded by this function nu. There is a function nu for primes that is orthogonal to all these guys of this form. This is what I would have wanted to take, but the only problem is that if I took this thing, then these guys are not bounded functions. And for non-bounded functions, these decompositions don't work. The reason, well, I don't know. I can't explain. So I'm happy to explain it to somebody who's interested why this kind of decomposition theorem cannot work directly for non-bounded functions. But what one can do, and this is a really nice trick that was developed by Conlon, Fox, and Zhao. What the trick they notice is that if you take this collection, the same collection that I have over here, but now you take bounded functions. So I will write in orange, I will put this bounded by 1, and I'll call it f tilde. If I take bounded functions over here, then all these functions are clearly bounded, and the products are bounded. Everything is fine, and then I'm fine. So I can find a decomposition theorem. So can have a weak decomposition theorem. Having the function, representing the function f as g plus h, where this function h is orthogonal to f tilde, and g is bounded like I wanted before. Okay, but then the observation, and Conlon, Fox, and Zhao, they call it the densification, but because it's done kind of in a step-by-step way, but basically the observation is that if you start out with this decomposition theorem, you get an automatic upgrade. So automatic upgrade. It's like in the airport. Well, you start out with a regular ticket, so you start out with this decomposition. You can't get a better one it's difficult to get a better one if you don't start with a bounded collection of functions. But this h that originally was only orthogonal to elements in this f tilde over here is automatically orthogonal. H is automatically, maybe a different epsilon, but automatically orthogonal to f. Okay, I start out with a weak decomposition theorem. I start with some class of functions, and automatically I get that this weak decomposition is automatically a much stronger decomposition. And for a stronger decomposition, it tells me that I can write, once I have this decomposition, that I have f equals g plus h, and g is bounded and has the same average as f, then one can apply Semrelli's theorem. So I think, well, I wrote I was going to talk about these narrow progressions and primes, and then I started writing the talk, and I thought maybe I should talk about decomposition theorems, but then I couldn't make it, which is different, like a very big, there's the decomposition theorems, there is a big class of theorems that is general, that is true in a very general context, not in just the pseudo-random context, but in a much general context. And, but then I realized that it's very difficult to do in an hour, so I descended to here, but I couldn't descend it to narrow progressions and to the decomposition theorem that works for the primes. But I do very, very much recommend this. There's a paper by, well, I didn't read the paper written by the 4 computer science people because I don't understand computer science language, so it's easier for me as a mathematician to understand Gauer's paper. So if I recommend for, it's a really nice paper about decomposition theorems explaining this philosophy of how, in which situations you can decompose your function into some, how can you make this projection idea work? And if you're a computer scientist, then I recommend reading it in the Tulsiani, Trevisan, Vadhan, and Reingold paper. And if you're a mathematician, I recommend reading Gauer's paper. Yeah, but if you read those papers and you get a good hang of what these decomposition theorems mean, and I think it's a very important concept in trying to calculate any average that you might be interested in calculating in your academic life, and then there are these extra tricks. But right, okay, I'll stop. So it kind of depends. So for example, these averages that I talked to you about before, these averages f of x plus r, these guys, these actually can be shown to be sitting in to be close to this function g of x. G of x is close to a bounded sum of exponential functions of e to the 2 pi I elements like these. So these functions are kind of close to linear functions. And if you add this over here, then these functions are close to what are known as nil sequences and kind of more complex. If you make these, the longer you make these, the more complicated your subset of functions may be, but they're still, at least in this specific averaging theme, they're still quite structured. But you can take any averaging scheme you want in any context that it comes up and ask yourself, I can rewrite this average as an f times the inner product with something. Ask yourself, what is this? Does this something, there's a good chance if this average would bring you into a smaller class of functions. Can you understand? Maybe you can describe the structure exactly, or maybe in here you don't really need we know that this G is much more structured than what I wrote over here. Actually, this G has this property that it's kind of at least locally looks like a nice sum like this, but in general you can just ask this take your favorite average or kind of averaging scheme, ask this kind of classification question, and in the combinatorial form, you have this machinery of decomposition theorems. So decomposition theorems tell you that automatically what you need to understand is this averaging, this space of averaging. Yeah.
So right now, there's no way to bridge this Maynard-Zag results and this.
Well, they definitely can't work for things that are true for any subset of primes. So it rules this type of thing out. If you can use some averaging scheme there and maybe something that is weaker, then I don't know. So over there is also some averaging that is going on. So every time you have an average, you can ask if you improve your situation by averaging, usually you do improve your situation and everything by averaging. So
Okay, so I just want to remind everybody that at 4 o'clock we will have an open problem session. And you can, if you didn't send the email already, you can just decide on the spot.